Greetings everyone. On the bench today I have a couple of my favorite audio amplifier ICs. Well, I have a few, but these are one of them. It's the TDA1517, and they're actually stereo amplifier ICs, so there's two amplifiers in one package, so it helps it make it easy to use. About 5 years ago I reviewed these chips, but I want to do it again, this time solder it up on the board, give a proper schematic and layout, run through the tests and see how good these things really are. These are nice chips if you want more power than something like an LM386 or the 1 or 2 watt amplifier ICs. These things can give you a clean 5 or 6 watts depending on the supply voltage, and a little bit less at 12 volts. And again, we'll run power tests on these things and see what they can deliver. The gain is fixed internally at 20 dB, which is kind of low, so they're really meant for line level inputs. If you use these with a device that has a headphone out jack, the voltage delivered may not be high enough, though some devices like my FiO player deliver plenty of output voltage, which would drive these things. And it operates in the 12 volt range, specified from 9.5 to 18 volts, but I would say 12 to 16 volts. Of course, it has various short circuit and thermal protection, and having that fixed gain, there's no external feedback components, resistors and capacitors to worry about, and that helps keeps the external part count low. These come in two. Actually, there's more package types. This is a single inline package with a heatsink tab on the top. This is the dual inline package. Yeah, similar pin out, actually the same pin designations. The top row of pins are all heatsink pins, so you can put it on a board with a large area for heat sinking. And one thing about these chips is that they use heavier pins. I don't know if you can see that. They're thicker than your standard integrated circuit pins because they have to dissipate heat. Let's take a quick gander at the datasheet here. Here's some of the features of it. Now it does say the supply voltage goes as low as 6 volts. However, it has this corny mute/standby type circuit which limits it to 8.5 volts or so. So unless you supply the mute circuit with more than 8.5 volts, it won't work down to this level. So that's kind of a shame you can't use it at, say, 9 volts. That's why I consider it a 12 volt amplifier, because if you run it on batteries and as the batteries run down, you need some headroom to operate. It says typical 40 milliamps. I think I said 45, but different data sheets give you different numbers. Texas Instruments also has this chip in surface mount, and their dual inline package is 20 pins. It's pretty much the same, but they have an extra set of pins on each side. And I really like that its repetitive peak current is rated at 2.5 amps. That's very good. And gives you some input specifications, input impedance. Here's your pin outs. More specifications here. Here's what I was talking about, that mute circuit. So you have to have that pin at 8.5 volts for it to work. So if your supply voltage drops below that, the chip stops working, even though the actual amplifiers can run down to 6 volts. So yeah, I'm never happy with these corny mute standby circuits they use. At least you don't need anything. You can just connect it to the supply rail without using capacitors or some intricate circuit to make it work. But anyhow, here is the circuit. Besides the supply of bypass capacitors, you really only need 5 capacitors for a stereo amplifier. You have your SVR cap, your input caps, and the output caps. There's no Bouguereau cells or anything like that. Okay, so the next thing is to solder this thing up and start running some tests. And here we go. We have a little board soldered up. For heat sinking, I put this copper tab, and then I put this 3M thermal tape so I can attach a heat sink. And I dug around and found this, and this fits in there. Have to watch that tab so it doesn't short. It's touching the ground anyway. Yeah, not really practical, but it's just to get through this video. This board is just mainly to go through the video. It'd be better to use the single inline version for this type of use. If you have boards made, then you could actually put a big copper area on there for heat sinking. You still might need to add a heat sink. You see this chip, if we can get 6 watts per channel, it's going to dissipate quite a bit of power. I don't know, maybe like 8 or 9 watts of heat, because we've got 2 stereo channels there, or I should say 2 channels for stereo. So yeah, don't underestimate how much heat this little chip can put out, because it is stereo and it can put out a decent amount of power. Let me show you that tape real quick. I really like this tape, but you do have to be careful. You can only dissipate so much heat per unit area. It's the 8810 3M tape. They have different thicknesses for, the thinner type for better heat conduction. But I like to use that tape for mounting these these little cob LEDs onto these aluminum boards. I just love these LEDs. I make more videos about them, but people go, man, this is an audio channel. LEDs. But anyway, yeah, so let me get that attached, and we'll hook it up and play some music. But first, here's the layout I used. Now this is, if the board, of course the heat sink's smaller, but if the board was sitting like this, looking down through the board to the connectors, it's easier for me to draw it like this because I'm familiar with the pin numbers and how the components sit. And this is the schematic using the actual pins on the chip, how you would connect things up here. So I utilize the signal and power grounds, just have the input grounds and the supply voltage rejection cap connected to the small signal grounds, and of course the power ground where the output return and the supply return go. And of course I use the low pass filter on the input to keep RF out of the amplifier, help reduce chances of high frequency feedback as well. So enough of this, let me get it hooked up and we'll play some music through it. Okay, I have it hooked up here. Power is on. I'll give you a music sample. Can't play much of that. Don't want to risk a copyright snag. That's the stuff I'd rather play. That's Bang, one of my favorite bands from the early 70s. But let's find something I can play here. turn that down. The music player decided to lock up. Well, now it's doing something. It wouldn't stop playing there. It won't stop. I don't know what its problem is. But anyway, yeah, that's some YouTube safe music. That sounds pretty good. Okay, what about noise? Probably can't hear that. It's very low. If I put my ear up to the tweeter, I can hear just the faintest background hiss, which I would expect. I mean, the gain is set pretty low on this amp. So yeah, no problem with noise. It sounds pretty good to me. Well, let's move on to the power test. Okay, I set up for the power test here. Using that amplifier resistive load that the viewer sent in to me. I really appreciate that, but I did want to improve it somewhat. I got rid of all that solid core Romex house wiring stuff and put this wiring in. I set these boards vertical so the heat can rise off of them. One thing that should be done though, see how the resistors are hugging the board? They really should be stood off the board a little bit. That way you can get heat all the way around them and they won't bake the board. You know, for example, this amplifier here. See how those power resistors are off the board a little bit? That helps dissipate heat and doesn't let heat dissipate into the board too much. But anyhow, this will be handy. You know, up position is 8 ohms, down is 4 ohms. And if I need more power, I can parallel channels. So if I need higher power 4 ohms, I can set this for 8 and then parallel these two channels to double the power dissipation. And if I need more power for 8 ohm loads, I can put it in the 4 ohm position and series the channels. So per channel I can probably do around 50 watts of short-term test, or yeah, around 50 watts, and for longer term maybe 25, 30. So now I use these banana plugs here I can connect the scope up to. Like also if I'm doing like a step response I can hook a capacitor up. But this is an example of buying crap gets you crap. These cheap banana plugs. See, you plug them in and they're loose. Crappy connection. These little springy things, they don't clamp down when you plug them in. It's just more junk from China. Yeah, you think you're getting a good deal, but you're just buying junk. Now I have these here. These are much better. I'll probably have to end up using them. But just another example. You buy junk, you get junk. Okay, anyway, let's move on with the test. What I'll do here, like always, I'll just test it at one supply voltage and one load impedance or resistance. And I'll do the rest off camera because it's just going to be boring, repetitive stuff. Okay, here we go. 4 ohm load, both channels driven. Let's get this thing set up. Okay, there's clipping. Very nice symmetrical clipping. I love to see that. I'm not seeing any oscillations. I'm not seeing rail sticking issues. Very good so far. So let's dial out the clipping. Right about there, I would say. Now to get the voltage measurement, I have to put more waveforms on the screen. At least the way this scope works. 3.32 volts. So 3.32 volts RMS squared divided by 4 ohms is 2.75 watts. So that's very good. This is right at 12 volts, and that's what I like to see. decent output swing. This is what I consider a third generation audio amplifier IC, where it has less parts. You don't need bootstrap capacitors and compensation capacitors and all that stuff. Yet you get good output swing. So I'm letting it run here. I'm just going to see how hot the chip gets. And it's getting warm. It's not burning my finger or anything. The heat sink's getting warm. I was kind of concerned that that little heat sink is not that big. Yeah, I got to do some higher voltage tests, so I'll have to keep an eye on that. Okay, we'll use the FFT mode on the oscilloscope here to take a look at distortion. So as usual, we have the 1 kilohertz fundamental. This is the 4.5 kilohertz pilot signal that I add in. It's at 1% of the amplitude of this signal. And the reason I do this, we caught it on a reset there. The reason I do this is it just gives me a reference of what 1% would look like, so I can see the other harmonics around that. I know I say that in every video, but I can't assume that everybody sees my other videos. So anyway, it just gives me a reference point. This here to the left, this is near 0 hertz. Each step is 1 kilohertz. And I believe that's what they call 1 over F, or thermal noise. That's always going to be there. It's just physics. And that's really nothing you can do about that. But we care what's to the right of the fundamental. And at 2 kilohertz, we're getting a little node here. I'd say it was about, 60%. So like 0.6%. A little disappointing to see, I guess, but we're not getting really anything else. Maybe the tiniest blip here. A low order harmonic at that level is going to be pretty much inaudible. Some people like the single-ended tube amps that have several percent of a second order harmonic. It gives that so-called warm sound, as they call it. But, I like my amplifiers to have low distortion. Though I really doubt I could hear that in anything. Okay, so using the Field Tech function generator, we will do a frequency response analysis here. So let's get pointed at the screen. So what I need to do is fine tune this. I need to get this at that graticule and that at the other graticule. Okay, we're good. So now I'll go over to the frequency. This is our base point at 1 kilohertz. And right now we're at 8 ohms. And there's been some sort of connection issue with this thing. But anyway, I'll drop the frequency. Recompensate for that. So we're at 100. Starting to see the slightest drop. Now, if I check at 4 ohms, you can see more of a load will pull that down a little bit. Let's go back up. 1 kilohertz. And 4 ohms barely makes a difference. Slight drop. So what's happening is the output capacitors, I'm using 1000 microfarad, they're starting to take effect at the lower frequencies. So we'll take her down. Oops. I got to switch over to that digit. So we're at 40 hertz now, and see a much larger drop with the 4 ohm load because of the capacitive reactance. That was still pretty good. I'll continue dropping. So right around 30 hertz. That's 20. So maybe right around 26 hertz or so would be the 3 dB drop-off point at 8 ohms. And at 4 ohms, let's see what that would be. Just eyeballing the screen here, I would say about 50, which makes sense. It would be around double. Okay. We'll go the other direction then. Start cranking this thing up. 10 kilohertz, it's flat. 20 kilohertz is flat. 60 kilohertz, you're starting to see a little bit of a drop. And at 100 kilohertz, we're off slightly, but you know, it's going to be flat way out there. Pretty typical of a solid state amplifier, negative feedback and all that stuff. So yeah, we do see the roll off at the lower end due to the reactance of those output capacitors, and just a nice flat frequency response on up from that. Okay, here are the results of the power test. So we started at 12 volts. We got 2.75 watts. At 8 ohms we got 1.59. And I won't read all of these, but the lowest voltage I can run this at is 9 volts. You could actually go down to 8, but it's starting to get a little bit low. Because of that mute circuit, you can't run it any lower. If you supplied the mute circuit the right potential, the amp would run down to 6 volts. But like I say, those goofy mute circuits they use. But anyway, at 4 ohms we got 1.44 volts. So the output swing is pretty well optimized. I'm getting good output. I'm getting good output power readings from the thing. At the maximum voltage I would recommend running it at, I'm getting 5 watts even at 4 ohms and around 3 watts at 8. One interesting thing, when running the amplifier on a regulated supply, I've always found that when comparing 4 and 8 ohm loads, the 8 ohm reading will be somewhere around 60% of the 4 ohm power reading. It's not 50% because there's additional losses, but I like to see around 60%, and that's what I'm seeing here. Frequency response is what I would expect. It's flat, except for the lower bass regions because of the output coupling capacitors. You could use larger ones, but you have to think about what your speakers can actually reproduce and if it's really reasonable to do so in a small amplifier like this. Quiescent current, which means the idle current with the amp turned on but not reproducing any signal, is 50 milliamps. So for stereo that's fine. It's good for batteries. Low noise, no issues there. Like I said, the gain is a bit low, so it could be an issue with headphone type music players. What you have to do is test your headphone music player, see if at higher levels it can put out a high enough signal. Like my new FIO player that actually puts out a line level signal, it would work fine with this amp. One minor disappointment was the distortion. I was getting about 0.6% second order harmonic, though the audibility of that is very debatable. And I wasn't seeing any weird things like notches or oscillations at clipping. So all in all, a very good amp. I really like it. Considering having boards made for this thing, might have to use the TPA version. It has more pins, has like an extra set of pins. So I have to check the output or the pin out to make sure it will fit if I'll have to rearrange the layout of it or not. But yeah, like I say, it's a nice little amplifier if you need a little bit more power. Plus you need something simple for stereo. I know some people are going to say, just use something Class D. Well, yeah, that's fine. If I was a product designer, I would certainly use Class D because, that's the going thing now. But personally, I am a Class AB guy. And I still like these Class AB chip amps that are hanging on here. Well, that's going to do it for this one. Really appreciate you watching and your support, and we'll catch you on the next video.